In this video of the Fundamental of Electrical Circuits series, what we're going to do is we're going to focus on looking at a fully connected transmission line, a three-phase, fully connected Y to Y circuit. Y meaning there is a Y source connected to a Y configured load through a bunch of transmission lines. So first, let's go ahead and talk about some definitions, if you will. So as we mentioned before, since this is a Y-connected source, and this would be a neutral line represented by small letter n. And sometime when you this node, even though it's not an essential node, we in many cases we will label it so we can have a conversation about what it is. And typically this is called the B prime to be distinguished from B, and this is referred to as A prime to be that, and then C prime to be distinguished from that. And then these ZGA, ZGB, and ZGC are kind of the winding capacitance, inductance, and resistance that is inherent in any source, anything that generates electricity. It will have some impedance attached to it. So these are referred to as the internal impedance of that particular generator. And as you can notice, then each one of these generator, when the wires comes out, this is the first time it comes out of the generator itself or the source itself, then it's connected to the transmission line. These transmission line could be anywhere from few miles to hundreds and thousands of miles, and then in this particular case there will be 4 transmission lines, and then of course they're connected to the load. And as you can see, the loads, we use a capital letter A, capital letter N, and capital letter B, and capital letter C to refer to the connection to the load. And of course the loads will be referred to as load A, load B, and load C. Now at this point, our focus throughout this chapter is going to be a balanced three-phase circuit. If that's the case, then the voltages VA, magnitude of VA must be equal to magnitude of VB, must be equal to magnitude of VC, because if it's balanced, they all have to have the same magnitude, of course same frequency, and they have to be 120 degrees out of phase, as we've talked about in previous videos. The other thing that is really important for us to know is if it's going to be a balanced three-phase circuit, then all the Z's, ZGA must be equal to ZGB must be equal to ZGC. Not only that, all these transmission, all the Z of the transmission line must be equal. So this must be equal to that. All of these must be equal to each other. So Z transmission should be the same. So ZTA must be equal to ZTB, must be equal to ZTC, must be equal to Z transmission N. Same thing for the loads. Z of load must be the same. So ZLA must be equal to ZLB, ZLC. And that's a prerequisite for having a balanced source. The reason it's important to have a balanced source is in order for the maximum power delivery and efficiency and all that, that has to be true. Now, as we have talked about before, if we have a perfectly balanced and these voltages have the same magnitude and they're 120 degrees out of phase, then we usually can say V of n plus V B of n vector wise V plus VC of n equal to 0. So if you sum all of them, the voltage is totally equal to 0. The other thing is these loads. Sometime you may see Z load referred to as Z phase load, which is basically say each one of these from here to here is referred to as one phase, and they usually show it with a phi. This is one phase, okay? if they're talking about line to line, they're talking about from here to here, here to here. So A to B, this is called line to line. So you could have A to B line to line, B to C line to line, or you can have A to B. But phases are A to N, B to N, and C to N. Okay, so the concept of, so here is what we got to do. We have to have a concept of a phase voltage, and usually they're thinking of, let's say, load phase voltage, and that would be, for example, here would be VAN. Okay, so and they're gonna have the similar behavior as the source have. In other words, all the load phase voltages will be equal to each other. All the phase currents will be equal, except the magnitude will be equal to each other, except they will be 120 degrees out of phase. And this is referred to IAA, IBB, and ICC are referred to as phase current. Okay, and in a Y connected, the phase current is equal to line current. Okay, but load voltage and phase voltage are not equal. That's a really important concept to remember, because VAN is not equal to VAB, but IAA, which flows through here, also flows through the phase, also is the same current that flows through the line, so they're said to be equal to each other. Okay, so that brings us to where we can now have a conversation about how do we do analysis on this one. So typically, if somebody says, hey, I want you to find the current in phase A, which means they want you to find this current in here, yes, you can draw the whole circuit and do it, or you can simply, instead of having to draw this whole thing, you can start by just looking at one phase at a time. And typically we look at the first phase. So if you look at it, I'm going to basically take this phase A. I'm just going to take that, everything that it has. So it has VA prime N, and then I'm going to have ZGA. Then I'll have the transmission Z transmission A, and then Z load A. And then I'm going to notice this is N and this is N. But if you look up here, we got a whole bunch of stuff that Zn is connected to. We don't need to show this, because by definition, the current that flows, because you're going to have the IAA come through here, you're going to have IBB come through here, and you're going to have ICC coming through here. By definition, some of those are equal to 0 because they're 120 degrees, much like the current, the voltage phasors was adding up to 0. We can the voltages add up to 0. We can also say that IAA plus IBB plus ICC in a balanced circuit, it's equal to IN, and it's equal to 0. Okay, so the neutral side in a balanced circuit, it will have 0 current flowing through it. I'm only going to have current through it if something is failed. So therefore, we don't have to show ZTN. So the beauty of this is, if you tell me what the generator in the reference is producing, I can tell you what this current is. This IAA is the phase or line current. I can also tell you what the phase voltage. This is a phase voltage. So sometimes shown as this. So it makes analysis a lot simpler. Now we can apply our KCL and KVL to the more complicated circuit up there, but I much rather do that. And once I have found VAN, all I have to do is shift this one by 120 degree one way or the other, and then 120 again to either find VB, VC, or VC, VB, plus 120 to get that, minus 120 to get that. So if this was, let's say, V phi angle of 0 for VAN, then VBN would be V phi angle of minus 120, and VCN would have been VP angle of plus 120 in one phase sequence and the reverse on the other phase sequence. This is called, they refer to this one as a single phase analysis, and is used quite a bit when we are analyzing these circuits, which allows us to do a third of the circuit, just to reference the VA portion. And once we found the values, we just shift them to find the value for the other one. Makes life a lot easier to analyze and deal with. Okay, that brings us to the end of this section where we talked about a Y to Y connected circuit, and also talked about the single phase analysis of such circuit. Again, all of this was mainly in the context of a balanced three-phase circuit, where it means all the phases are equal except they're shifted by 120 degrees.